A transmission tower, also known as an electricity pylon or simply a pylon in British English and as a hydro tower in Canadian English, is a tall structure, usually a steel latticed tower, used to support an overhead power line. In electrical grids, they are generally used to carry high-voltage transmission lines that transport bulk electric power from generating stations to electrical substations. Utility poles are used to support lower-voltage subtransmission and distribution lines that transport power from substations to electric customers. They come in a wide variety of shapes and sizes. Typical height ranges from 15 to 55 meters span between the islands Jintang and Sezi in China's Zhejiang province. The longest span of any hydroelectric crossing ever built belongs to the power line crossing of Amaralik Fjord with a length of 5,376 meters. In addition to steel, other materials may be used, including concrete and wood. There are four major categories of transmission towers: suspension, terminal, tension, and transposition. Some transmission towers combine these basic functions. Transmission towers and their overhead power lines are often considered to be a form of visual pollution. Methods to reduce the visual effect include undergrounding. Transmission tower is the name for the structure used in the industry in the United States and some other English-speaking countries. The term electricity pylon or simply pylon comes from the basic shape of the structure, an obelisk-like structure which tapers toward the top, and the name is mostly used in the United Kingdom and parts of Europe in everyday colloquial speech. This term is used infrequently in most regions of the United States as pylon commonly refers to other things, primarily traffic cones. In the United States, the use of the term pylon is more common in the Midwest, including areas such as Cincinnati and Chicago. In Canada, the term hydro tower is commonly used as hydroelectricity constitutes a majority of the country's energy production. Three-phase electric power systems are used for high-voltage transmission lines too. The towers must be designed to carry three conductors. The towers are usually steel lattices or trusses and the insulators are either glass or porcelain discs or composite insulators using silicone rubber or EPDM rubber material assembled in strings or long rods whose lengths are dependent on the line voltage and environmental conditions. Typically, one or two ground wires, also called guard wires, are placed on top to intercept lightning and harmlessly diverted to ground. Towers for high and extra high voltage are usually designed to carry two or more electric circuits. Circuits are initially installed. Some high voltage circuits are often erected on the same tower as 110 kV lines. Paralleling circuits of 380 kV, 220 kV and 110 kV lines on the same towers is common. Sometimes, especially with 110 kV circuits, a parallel circuit carries traction lines for railway electrification. High-voltage direct current transmission lines are either monopolar or bipolar systems. With bipolar systems, a conductor arrangement with one conductor on each side of the tower is used. On some schemes, the ground conductor is used as electrode line or ground return. In this case, it had to be installed with insulators equipped with surge arresters on the pylons in order to prevent electrochemical corrosion of the pylons. For single-pole HVDC transmission with ground return, towers with only one conductor can be used. In many cases, however, the towers are designed for later conversion to a two-pole system. In these cases, often conductors on both sides of the tower are installed for mechanical reasons. Until the second pole is needed, it is either used as electrode line or joined in parallel with the pole in use. In the latter case, the line from the converter station to the earthing electrode is built as underground cable, as overhead line on a separate right-of-way or by using the ground conductors. Electrode line towers are used in some HVDC schemes to carry the power line from the converter station to the grounding electrode. They are similar to structures used for lines with voltages of 10 to 30 kV, but normally carry only one or two conductors. AC transmission towers may be converted to full or mixed HVDC use. to increase power transmission levels at a lower cost than building a new transmission line. Towers used for single-phase AC railway traction lines are similar in construction to those towers used for 110 kV three-phase lines. Steel tube or concrete poles are also often used for these lines. However, railway traction current systems are two-pole AC systems, so traction lines are designed for two conductors. These are usually arranged on one level, whereby each circuit occupies one half of the cross arm. For 4 traction circuits, the arrangement of the conductors is in 2 levels, and for 6 electric circuits, the arrangement of the conductors is in